Yeah, so you compute the divergence of that vector. Okay. If it is positive, then something is diverging. Okay. If it is positive at a point, if it is positive at a point, then from that point, there is some source. Okay. So the some quantity is diverging. Okay. So we'll actually see better physical interpretation of divergence when you learn a so-called Gauss divergence theorem. Okay, so we'll see that this quantity, uh, uh, essentially this quantity, I need some space, is actually gives a flux. Okay, so if there's a net flux through a surface, that means that there is some source inside the surface. Okay, so we'll see some more physical significance of divergence, but to check whether there is whether a point has a divergence or convergence. Okay, that you can easily check by computing the divergence of that of the vector. Okay. So yesterday I was taking this example that a equal to x square x cap, and if you plot that, then you find that on the left side, so this arrow represent the vector a, okay, at different x value. Okay? So obviously at x equal to 0, the value is 0. Okay, so it becomes a null vector. Okay. By the way, so yesterday someone asked what is null vector? I mean, why can it have a direction? Okay, so the good point about the null vector is that you can add another vector, okay, with a null vector. So it is a valid operation. Okay. So later when you learn the vector space, so there you real null vector represent a vector space. So like a operation, I mean, you cannot add a scalar with a vector. Okay, you have to add vector with vector. You have to subtract vector with vector. Okay, but if you have a null vector, you can still add or subtract. Okay, with another vector. Yes.
Sir, yesterday you gave us a problem for a function 1 by r.
Yeah, I'm coming to that. Okay, so with this one, you agree that this will be the arrow. Okay, on when x is positive, quantity is pointing, the vector a is pointing towards the right, and the value increases with x square. Okay, as the x increase on the left side, it is pointing. Oh, okay. So yeah, so okay. Okay, I made a mistake. So when x is okay, so it is x square. Okay. So it is still
Still points in the direction of x.
yeah. I made a mistake.
Yeah,
Yeah.
direction is opposite.
Yeah.
Magnitude
So
is right.
like now I have to just correct these arrows. Okay. And when I correct these arrows, okay, it will take time, but you understand. Okay. You have to correct it. Okay. Uh, so then you see that if you go from left to right, okay, so that is with increasing x, the quantity actually decrease. Okay, so here from left to right, if you increase x, the quantity increase. So there's a positive divergence. Okay, so there's some net flux. Later you will see that this also represent some amount of flux. Okay, and that is possible when there is some source. When there is a source in some region, you will get divergence. Okay, the quantity will diverge. Okay, if there is a no source, if there's a sink, okay, then the quantity will converge. Okay. So source sink concept will come in next week. Okay. Okay, so here from this plot, you can now convince yourself that when you go from left to right, the quantity decrease. You see the arrow or the magnitude, you see the quantity decrease. Okay, so here you have a negative divergence. Okay, so del dot A is less than 0, and here del dot A is greater than 0. Okay, and what was the homework problem that I gave? What function I gave?
F equals to 1 by R.
1 by R.
Okay, so yeah, so
Sir, it's pointing away from the origin.
yeah, 1 by R. Okay, so you see this is and then I asked like what is grad A, right? So this will be minus R cap by R square. Okay, are you sure? Or you can write this minus vector R by R cube. Okay, R cap is the vector of unit position vector. Okay, so you see that it has I mean the gradient actually is decreasing, and so basically, so this is a vector. Okay, now this is a vector. Okay, so the direction of this vector is pointing towards the center. Okay, towards the center, and it is and its magnitude actually increase. So when R decrease, this magnitude increase. Okay, so the magnitude increase. Okay, so at origin, actually this quantity blows off. Okay, you have very large value. Okay, so this again says that there is a some net net okay, so there's some net sink. If you compute divergence of this quantity del dot del F, this one, yeah. So you can compute this quantity. I just again leave it to you. Okay. It is not not that easy. Okay. But I'll come to this point later also. But if you are curious, you can do it by yourself now. Okay. And later you will compare the result. Okay. Okay. So now let me come to. Okay. So so in exam we sometimes give problem that you represent a vector. So we give some vectors and you ask to represent them pictorially. Okay. So you have to keep two things in mind when you draw a vector: the direction and the magnitude. Okay. So magnitude you have to set with the length of this arrow. Okay. And the direction also you have to keep in mind. Okay. Okay. So now I'll discuss the curl. Okay. What is curl? So curl is again a vector quantity. Okay. So we had a grad of a scalar quantity, and then we gave the divergence of a vector. Okay. Now we have this curl. This is equal to this one. Okay. Del cross product with a vector. Okay. So this is the curl. Okay. So curl is meaningful only when we have a vector quantity. Okay, we cannot write like a del cross a scalar quantity, Okay? But again, like the divergence, the this quantity is not is equal to a cross del. Okay, obviously the cross product do not commute and but here again this will be a big mistake because this is again an operator. Okay, but this is a valid quantity, by the way. Okay, when you do a lot of vector calculation, you will see this type of term. Okay, this is a valid term, but the point is this one is not equal to that one. Okay, so again sorry, this is a valid term. Okay, when you do a lot of vector calculation, you will find a term which involve this quantity. It's fine. This is the valid term, but this one is not equal to that one. Okay. So similarly, this one is not equal to that one. Okay. Now, what is curl? Now, again, by the curl, you already get some idea about I mean this quantity. So if a vector, so again, this is a vector. In general, I'm taking this vector as a non-constant. Okay, it depends on space. So a different location in the space, you'll have a different magnitude as well as different direction. Okay, so sometimes we can have the vector which has like a rotating pattern. Okay, it has a the vector will rotate around a point. Okay, so like the air flow in the air. Okay, so when the tornado occurs, so it's mainly because of this rotation of the earth. Okay, earth rotate, and because of that rotation, there will be the flow in the air in our earth atmosphere experience Coriolis force. Okay, and that gives some sort of twist, and it make produce some sort of rotating flow. Okay, it may not be global flow, but it can be some local rotating like spinning like flow. Okay, that will be produced, and in that region there will be a non-zero curl. Okay, so how to okay so let me. So the physically this curl says that how much vector rotate around a point. Okay. So I'll take an example. So take this a simple, very simple vector. Let's take it 2D. Okay. So let's take it minus y x cap plus x y cap. Okay. A simple vector. Let's see its pictorial representation. What I'll do, I'll use this space. Okay, so z-axis is perpendicular
Sir,
to the board. Yes.
sir, there is not a name for a vector cross del.
A vector cross del. No, it has no name. Okay, it has no name. But you will see this type of term. Okay, it's an operator. Okay, it's basically like a cross product of two vectors. So del is a vector, but it's a vector operator, and A is the usual vector. Okay. Okay, so now let's represent this vector A. So take x equal to, let's take this point, x equal to 1, y equal to 0. Okay, x equal to 1, y equal to 0. So at this point, x equal to 1, y equal to 0. Okay. Oh my God. Y equal to 0, x equal to 1. So you have y cap. Okay. A you got is equal to y cap. So this much length is my unit 1. Okay. So this is y cap because this is y direction. Okay. Now take so let me take this point, x equal to 1, y equal to 1, x1. Okay, so minus x cap plus y cap. So what will be the direction here? So it is basically it is pointing this and this, right? So it is the resultant of that. Okay, so I'll remove this. So at this point, the vector will have. My drawing is not that perfect, but you understand what I mean, right? Roughly correct?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, very
Yes,
good.
sir.
Okay, now you take this point. Okay, so this is my, okay, this point. This point is x equal to 0, y equal to 1. A is how much? A is minus x cap. So minus x cap is this direction, not that long. Okay, very good.
Yes.
And then let me take this point. So this point means x equal to minus 1, y equal to 1, x equal to minus 1, y equal to 1, x equal to minus 1, y equal to 1, x equal to minus x cap minus y cap. So this will be this and then that. So the resultant will be this. Again, roughly correct. And then now we'll take this point when x equal to minus 1, y equal to 0, x equal to minus 1, y equal to 0. So you have minus y cap is this direction. Okay. And now let me take one point here and then I'll complete it. So at this point, x equal to 0, y equal to minus y cap, y equal to minus y cap. So this is x cap. Okay. You can take some more point. Okay. If you take more point, then you'll see that here again this way and that way. Okay. I just keep few points, but you understand. Okay. It's very obvious. You just take few points and then you'll realize. Okay. So this I took the magnitude 1. Again, if you increase the value, if you instead of 1, if you just make it 2, then you will have again somewhat bigger arrow. Okay. And then somewhat bigger arrow here, and then somewhat bigger arrow here, bigger arrow here. Okay. So you will realize that it is actually rotating like this. Okay. So there is a like a spiral type pattern around a point. Okay. So there will be a point around that. There is some something like curling type pattern. Okay. So how much vector a vector curl, okay, around a point. So that is the physical interpretation of the curl. Okay. So non-zero curl is means that there is some sort of rotation, okay, around a point or some curling, motion. So if A represents a velocity field, the velocity field is something called rotational velocity field. Okay. If the curl A is 0, if curl A, by the way, sometimes we write like this, curl A. Okay. Or in some people just write it like this, curl A, or you can just simply write it like this, curl A. Okay. Or you can write it just this. Okay. If curl A is equal to 0, then this A is called irrotational. Irrotational vector. Okay. Rotational, okay, and it's the irrotational. Okay. So if curl A is 0, that means the vector has no this spiraling type motion. Okay. It doesn't curl around any point. Okay. So that means it is a irrotational vector. Okay. By the way, I forgot one quantity when I was discussing divergence of A. If please add one small note when you're discussing the divergence. If del dot A is equal to 0, then A is called solenoidal. Yeah, so these are the meaning. For this. Okay, so this much is curl, a gradient, divergence, and curl. Let me take if you have another. Actually, in the book you will find. I think this example is already given. Yeah, minus y x cap plus x y cap. This is already discussed, and there is another. So if you see this figure in the book, you'll find this another picture which has a curl. But let me take a simple case. For example, let me take. Of course, if you have a constant vector means this magnitude, doesn't change in space or in time. That means the components of the vector also doesn't change. So basically, if it points along x-axis, then it will point along x-axis, and its magnitude also same, okay, at all point. So that is a constant vector. Then obviously for constant vector, the divergence will be 0. Okay. So nothing diverges, nothing converges. Okay, just uniform. Okay. Similarly, for this constant vector, the curl will also be 0. Okay. Similarly, for constant function, constant scalar function, the gradient also 0. Okay. So this thing very trivial. Let me.
Sir, what is invariance?
Invariance. Okay, invariance. I don't know where you have seen this term. Okay, because that depends on somewhat the context. So invariant we usually discuss like when you do the coordinate transformation. Okay, it's very useful term when you discuss the relativity. Because in relativity things change when you go from one frame to another frame. Okay, your time change, your length change. So invariant means when you go from one frame to another frame, if the quantity doesn't change, okay, then it's the invariant. Okay. So you remember I was discussing the coordinate rotation in the past lecture when some student missed it, but it's okay, it is not included in the syllabus usually. So for example, when you rotate your coordinate system, what happened? Your component do change, component of the vector change. Okay. But the its total magnitude of the vector doesn't change. Okay. So it again, so invariant you asked like what context you use, and my answer is that if the quantity doesn't change, it remains doesn't change under coordinate transformation, then the quantity is invariant. So obviously if it is scalar, then of course it doesn't change. Whatever the coordinate system you take, if it is vector, again the vector itself doesn't change, but their component do change.
And sir, what about the direction of that vector?
Direction of which vector? Oh, the curl.
Then no, sir, what you were saying that if the magnitude does not change, then we can say that is invariance. But
Okay.
what if the direction changes?
No, direction also doesn't change with the coordinate transformation. Okay. So if a vector, look, coordinates are the are like you have a vector, let's say A, okay, A vector, okay? And here is your coordinate system, x, y, okay? You can see this part. Now, if you rotate or translate your coordinate system, your vector will always point in that direction, okay? Of course, if you align your x-axis with A, then your A vector will be pointing along x cap, okay? But note that the vector, the direction of the vector doesn't change. Okay, only the projection of the vector along this coordinate along different axes will change. Okay, so if you align x with this vector A, then this A will have x cap only. Okay, the direction along x cap. Okay, but that's fine. But still the vector is pointing in this direction only. The coordinate system that we represent, we cannot change the vector. Okay, we cannot change its magnitude, we cannot change its direction. Okay, so one related thing I am missing, that what will be the curl of A? Sorry, direction of the curl of A is a vector quantity. What will be the direction?
Right hand thumb rule.
Yes. So if we have a I mean, here the right hand thumb rule is not useful in a sense, because I mean right hand thumb rule actually we apply when you have two vector A, let's say A and B, and the cross product we use. Okay. But usually what we check is that so curl, A has a direction. Okay, this curl of A will be perpendicular to A. Okay, now the point is upward or downward. Okay, it will be determined by the magnitude. Okay, if it is positive, then the usual notation is upward. If it's negative, the usual notation is downward. Okay. Later you will see that I mean, again you will see some meaning, some more interpretation of this quantity. Okay, when you have the integral theorem. In fact, tomorrow I'll start the integral theorem.
Sir,
Yes.
sir, can you explain about the solenoidal vector?
Solenoidal vector is a vector. So let's say this vector. Okay. So you have say A is equal to some vector r cap by r square. Okay. So this magnitudes are like this. Okay. This magnitude decrease. So magnitude is decreasing. Okay. My handwriting is not that good, but at least you get some idea that magnitude is decreasing and it has divergence. Okay. Okay. So if you take some surface, three-dimensional surface around this origin, you realize there is some net flux. Okay. Again, I'll discuss the flux after I discuss the vector integration. So you see something is converging, from this point. So this vector has some positive divergence. Sorry, I said convergence here. Okay, so it has divergence. The quantity is diverging, so it has positive divergence. But again, from this picture, do you see any sort of rotation? Okay. Is there any rotation pattern? Is there any curling motion? So what will be this quantity for this A? You don't have to compute this math. You can of course compute and do it yourself. It will be 0. It has to 0. It has to be 0 because you don't see any curling motion here. Okay. So it is a irrotational vector. Okay. So A is a irrotational vector. Okay. So later when you study the fluid mechanics or aerodynamics or meteorology, okay, in all this subject, this divergence, gradient divergence curve, very useful quantity. Okay, very useful quantity, because engineers always bother this quantity, curl of A. Okay. We like we don't like a rotating flow. Okay, because rotating
Sir.
flow get a lot of problem. Okay.
Sir,
Yeah.
sir, I didn't understand how to determine the direction of the curl resultant vector.
Direction of curl. Yeah, as I said that it is. I mean, it is obvious that it will be perpendicular to A.
Perpendicular thing. Yes, sir.
Okay. Now then it is upward or downward. Okay. How to say it?
Yes, sir.
Then you have to apply some convention. You have to apply convention. Okay. The usual convention is that if the quantity is positive, okay, then it's upward. If the quantity is negative, it's downward. Okay. And
Okay.
actually, so this ambiguity will actually will dismiss after I mean most likely tomorrow. Okay. So we'll have a better way to determine the direction. Okay.
Okay, sir.
So this gradient divergence curve will be using this course very frequently. So you have to be master in the vector calculation now, so that you can follow the mathematical calculation very easily. Okay. So sometimes we don't do the math, we don't do the calculation. Okay, like by seeing the vector, you can easily tell whether it will have a curl or divergence. Okay. So that confidence you have to grow.
And sir, how will you find the magnitude?
How will we find the magnitude? Okay, good point. Okay, so let me write this quantity. I have not written this this quantity explicitly. So curl A. So this is equal to. So obviously it will have three components. X cap will be del A, del y minus del A, del z. Here is z, here is y. Okay, plus y cap del A, del y z, del A, del x, ax, z, plus z cap del A, del z, x, y, x. So you can write this quantity in terms of a I mean in this way. So x cap, y cap, z cap, and then del x, del y, del z, ax, ay, az. Let me remove this. So determinant you probably have heard and probably have used also. So this basically, I mean, either you remember in this form or you remember in this form. Okay. So now the magnitude, then I mean, so like the divergence, sorry, gradient, we had a very easy way to represent, but here we have this, I mean, it's a vector, so you have to compute this mod, okay, the magnitude of this quantity, okay, the square root of this quantity, that quantity and that quantity. Okay. If the vector A is given, you compute this partial differentiation, and then you then you have a some resultant vector, and you have the magnitude and the direction. So what? Okay, so let me take a simple example. Give a very easy vector. Let me take an example. Can you give example? Simple vector.
xi cap plus yj cap plus zk cap
X I cap
plus
plus
yj cap
J cap
plus kk cap zk cap.
Z cap. Okay, you made my life very simple. I know this vector will have curl. This is a position vector. Okay, this will have curl 0. Okay, again this is based on my knowledge. Okay, because I'm little experienced. So, but let me compute this quantity. Okay, so A is this much. Now I'll compute. Okay, so I have this much space. So curl A x cap. Okay, now you say I cap, j cap, k cap. So I'm fine with this. I cap. Okay, so AZ has Z component. Okay, AZ has Z. AZ is Z, so it's 0 minus AY is Y, 0. And then AX is X. Okay, so derivative with respect to Z is 0. This one is AZ is Z, again 0 is 0, 0. Okay. So this is 0. Okay. This is actually the null vector. Okay. So I don't know how to put this. Okay. So you can still write is 0 if you are very,
Zero I hit.
yeah, it's basically null vector. So the curl A is 0. Okay. And it has, so it is irrotational. Okay. A is rotational vector. Okay. Now, if you make this a little bit, okay, I mean you can take a somewhat complicated example and do the math by yourself. But let me discuss few interesting points. Of course, all points are interesting, but let me write some. There are some. Yeah, I should have written all this formula somewhere, but you can find a complicated example, and if you have difficulty in solving in computing gradient divergence curl, or you have difficulties in understanding this physical meaning, you can also report me. Okay.
This represents a curl.
What?
Do we have a proof why this formula represents a curl? Is there a proof for that?
Wow. I can give a somewhat I can give a proof, but not today, because that requires integral theorem. So wait so tomorrow I'll give some, I'll discuss one integral theorem, and then
So we can calculate it by vector product, like cross product simply.
no. It is not. So this is a okay. So many of these vector this dot product and cross product rule will not work. Okay, things are not that trivial. Okay, I am actually looking for some of this formula. Yeah, I should have written down everything on a paper. Okay, so let me start. So this one. So formula number one. So this is a valid operation, right? F is a scalar quantity. You can call it scalar, general scalar field, right? Can you see the board clearly?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
This one is how much? So you can use this chain rule of differentiation. I mean, it's not exactly that chain rule, okay, but you can remember it that way. So you have to write this operation. So if you are not very sure how to take this operation, okay, so you just put things in a bracket. Okay, so you have a del operator. So this will operate on these two. Okay, so then you'll have this quantity plus the gradient of a scalar function dot product with the vector. Okay. Now, if you are not sure that this is correct, then you have to prove it by yourself. Okay? It's very easy. What you need to just do, this is just a scalar quantity. Okay? It's not a constant, but it is a space dependent. It can depend. It can be like x, y, z, or it can be x square, y, z cube. Okay, anything, any
Sir.
function, any scalar function. A is a vector function, vector field. Okay? And then the operation will be F will be out, and then you have a divergence of A, and then you have a gradient of the scalar function dot product with A. Okay. Now remember, this is now a vector. This is a vector. Okay. This is not an operator anymore. Okay. This one you can write is equal to A dot grad A. This is correct. This is correct because this has already operated. The del, this operation power is finished. Okay, because it has operated. Del has, del will operate on F. Okay, then it's just a vector, and then you have another vector. So dot product between two vector, is commute, can commute, and then you can write this. Okay. So someone was asking questions, but I did not listen. Tell me again now.
No, sir. Now it's clear.
It's clear. Okay, good. So again, this is scalar. So this is scalar. This is scalar. This side is also scalar. Okay. Now same thing, same type of operation you can do with this thing. Actually, I should have started. So let me call this first 2. Number 2. Number 1 is this one. Gradient. You can have a f and g. Right? We had taken gradient on one function. Okay, but you can have a product of two functions. So that one is very trivial. This is a chain rule. So you can take f out and then gradient on g plus you can take a g out, gradient on f. Okay, so I do not need this. So if you want to make some heading, then vector vector differentiation rule. Differentiation rules. Okay. Similarly, you can have another operation number 3 with curl. So curl we take with a, but we can have again a scalar function f that is being multiplied with r. This is equal to again you'll have the same thing. F will be outside and then curl a plus grad f cross a. Okay. These two are very similar. Okay. So f, this scalar function will be outside. Okay, and then you have the curl a, and then this f will operate. Del will operate on f. Okay, and then you have curl.
नेगेटिव साइन आएगा.
No negative sign here. Okay, if you interchange this, then negative sign आएगा. Okay, इसमें. If you interchange here, right? So again, if you don't believe me, you have to prove it. Okay, and so that this is wrong, right? Okay, so yes.
What is the difference between first and second point?
First and second. Okay, so this is a different operation. This is gradient operation.
Oh yes, sir. Yes.
Divergence operation. Okay, so let me take an example. Okay, so take an example. Like I said, A is equal to, let's say, vector R divided by R cube. Okay. Now you need to compute curl of this quantity. Okay, so curl A. How will you compute? Now vector R is a position vector x I cap plus y j cap plus z k cap, and then you have R cube. So then you have x square plus y square plus z square and to the power 3 by 2. Okay, on the denominator. But I am a lazy person. Okay, so I don't want to write those big formula. Okay, but I want to. Okay, again, if you just put all the value and then you expand, because curl has this big 3 term. Okay, 3 big term. And if you do this explicitly, of course, you will get the correct answer. But let me apply this formula. Okay. So then we have curl r vector by r cube. Okay. This one. Now you apply this formula. You have f. So f is what? Here. 1 over r cube.
1 by r.
Q is f, and then a is position vector r. Okay. So then we'll have 1 over r cube, and then curl r plus gradient of 1 over r cube cross product r. Do you agree? Now curl r is a position vector. Okay. It has I mean it will be 0. Okay. It is a position vector. It cannot have curl. Okay. That you should keep in mind. Okay. So that in a short time you can do difficult problem. Okay. So this is 0. Now this one. So I remember this formula. So I in my student life I used to remember this formula. R to the power n. This is equal to n r to the power n minus 1 and then vector r. Okay. If I'm correct, now I'm not a student anymore. Okay. In student life I used to remember. So this one will be minus 2, no, minus 3 r to the power 5 and then vector r. Okay.
R to the power 4, sir.
R to the power 4.
Power 4.
I think this formula what I wrote is not it may be to the
It's r to the power
No,
4
sir.
now.
R to the power n minus 1.
minus 1 and then r cap, I think.
Sir, here r to the power 4.
R to the power 4, sir.
In the
R to
denominator.
the power 4, sir.
So this one will be this one. Actually, today I don't have this notebook with me.
Sir, here n is equal to minus 3. No?
Huh? What?
Sir, here n is equal to minus 3 in that formula that you have written.
So, sir, you are right. If there was a 4, then it should be cap.
Minus 3 by r to the power 4.
You are right, sir.
Yeah. Anyway, you check it. Okay. As I said, I'm not a student anymore. you should do the hard work. Okay. So, but anyway, it doesn't matter if it is a 5, 4. You will get the correct. You'll get.
Yes, sir. Got it, sir.
Sir, your formula is like r cap.
Correct.
Okay. So now you have
Correct,
this
sir.
cross product with r. Okay, and it has to be 0. Okay.
Sir, it will be r power n minus 2.
R power n minus 2.
But then, sir, r cap will become r vector if it becomes r to n minus 2.
Yes, sir.
Yes, sir.
R
This is
vector.
right? Do you agree with this?
Yes, sir.
Okay, very good, very good. Okay, so then you got 0? You got
Yes,
0?
sir. Yes, sir.
There is nothing wrong. Yes.
Sir, what we have said for curl of r vector is similar. By the same thought, we can say for a vector also, na?
By the same thought, we can
For a vector also, na?
for a vector also. I did for a vector only.
Sir, by the thought through which we have calculated the curl for r vector.
Yes.
From the same thought, we can also say for a vector also, na?
Yes. Okay, so what I showed here, I mean that in some cases the application of this formula will actually make your calculation very easy. Okay. So and also sometimes easy to interpret your result if you expand in different form. Okay. So
Sir, how do we get that formula for a gradient of that scalar quantity? No, last line, that gradient of r to the power of n is equals to n into r to the power of that one. How do we get this formula?
This you need to prove. You just prove it. You do it. R is the position vector. You know, it has this R equal to square root of x square plus y square plus z square. You check it. Okay. N is any number. Okay. N is an integer number. You check it. You will get this value. Okay. Okay.
It is just like formula of normal differentiation, na sir?
Yeah,
R to
exactly.
the 1.
Yeah, exactly. But it is the, as I said, gradient is actually the extension of the normal differentiation. Okay. But when you have a normal differentiation, you
sir.
have only one dependence. You don't have to bother in which direction your slope is there. Okay. But you have a three-dimensional quantity. You have to bother like in which direction the slope, you know, you are computing. Okay. So that's why you this gradient is basically, you know, general description of differentiation of a function, of a scalar function. Okay. Okay, so we had three formula, and then we can have formula A del dot A cross B. Okay, del dot A cross B. This one again you have to remember. Del dot A cross B, this is equal to B dot del A minus A dot del B. You see the way I wrote. Oh my God. So this I wrote for the del. Okay. B cross curl A minus A cross curl B. Okay. B dot. I'm just doing the wrong thing. Okay. If you have the book with you, then you can just tell me. Okay.
I think the second one was correct.
B dot curl A. A dot curl B. Okay. Yeah. So this is correct.
Sir, this is the same as previous one.
No, it is not the same as the previous one. Okay, previous one is very much different.
Yes, sir. Yes, sir.
Again, this one and that one also too much different. So you have the scalar involved. Now you have the vector, because this is a valid operation. You have you can take a divergence of a vector. Okay, now because curl of two vector is a vector quantity, and you can take the divergence, right? So similarly, we can do another operation, gradient of this quantity, gradient of we can take only the scalar. Okay, so scalar you can form A dot B. Yeah, A dot B. Now this is a very simple formula. Okay, so grade of A dot B, that I will have a 4 term. Okay. So this is equal to B dot cross A minus A dot A of Okay, wait. Let me see. So, yeah.
Sir, same formula.
Yeah, it is not a trivial formula. So this you have to be very careful. Del of A dot B. I should find out this formula. Do you see this formula in the book? It is given. Yeah, it is given in the book. Now I'll copy it. Okay, so we have A cross curl B, and then we have B cross curl A plus A dot del B plus B dot del A. Yeah. And then you have another formula which is very similar to this one. This is equal to the curl of A cross B. What is the time now? Oh, the time is up. So I'll not write this formula. All formula are given. I'm just saying that these are important. Okay, so some of these formula are difficult to remember. Good thing is that now we have the open book exam. When you have the exam, your books are with you. But at least some formula which are not too difficult to remember. Like this one, you have to remember. This one, you have to remember. This one, you have to remember. Okay, and this one also you have to remember. Although I was being mistake. Okay, this one is a little difficult to remember. Okay, but again, like when you don't have open book exam, you have to remember.
जब 4 याद कर लेंगे तो 5वां भी याद हो ही जाएगा. Sir.
Yeah, there are actually few more, so I'll discuss in the next class.
Sir, gradient of A dot B को gradient of A dot B plus gradient of B dot A भी लिख सकते हैं.
Gradient of
Sir, fifth वाला.
Fifth wala. That you can do. Yeah, so that's fine because A dot B is fine. So here, this is a scalar quantity. Okay, this is anyway a scalar quantity that you can. Okay, so here also you can check it. If you just interchange A and B, your result will not change. Okay, you see the symmetric term. You make it A to B and B to A, then you will get this term. Okay? These two are identical terms. So actually, in the student time, when I was a student, I used to just remember only two terms. Okay, this one and that one, because the other two term will be just the you have to interchange A with B. Okay, so that's the correct point that you mentioned, that if I change A to, if you just change A to B, then will the result change? The answer is no, and that's why that's how I remember this formula.
Sir, you took sir. You took R vector, then it is a generalized form of sphere or any function.
R vector. So when I don't say anything, it is the generalized vector. Yeah, generalized position vector is basically radius of a sphere. Okay. Okay, radius of a general sphere. Okay, again, what is general? General means like a. I mean, you understand, like.
We cannot take any other vector instead of that.
No. In exam, you will see many problem. Okay, not many. Okay, but you may see the problem where this the formula is written in terms of R. Okay, and it will be written R is a position vector. Okay, or sometimes it is written R is equal to X I cap plus Y J cap plus K cap. Okay, but you have to when you say mention that is a position vector, you have to take its general form. Okay. You have to take its general form. You don't just do it like this. Okay. If I check the paper, I give them full marks. Okay, but you have to because I may not check all the paper. Okay, so you have to when nothing is mentioned, you have to take the general form. Okay, assume the 3-dimension. Okay.
Okay, sir.
3-dimension vector. Okay, so tomorrow I'll discuss few more identity and then I'll discuss the integral theory. By the way, do you have class now? Do you have class now?
So at 11 a.m.
So at 11 a.m.
Yeah,
At
then
11.
Can you do our this today's class at 9:30, 9:30 to 10:30? Then you'll have half an hour gap.
Yes, sir.
Good.
Yes, sir.
Yeah, it
Yes.
is good for me also. Okay, so so you have free 1 hour only in Wednesday.
Yes, sir.
Okay.
Yes, sir.
Okay, so then please note this time. I'll change the calendar also.
Sir, can I ask you something?
Yes.
Sir, are you fourth year PhD student?
Very good questions. By the way, when I joined this institute in 2018, so now you have online admission. So we had the offline admission, then a lot of students will come and then document verification. Okay, so this administrative, people actually need staff, and then they call us. So and then some student they just call, अरे भैया इधर सर ये हाँ भैया ये क्या है ये इस well, they just call me Bhaiya. Okay, so they also think that I'm a student. Okay, but I'm not student. I am an assistant professor in this department, and yeah, I have done my master's in physics from Indian Institute of Science, Bangalore, and my PhD is also from Indian Institute of Science, Bangalore, and then I spent few years in abroad. In Stockholm, Germany, and USA, and then I'm here.
Sir, but I remember in the first class you said that you're fourth year student. I just didn't remember.
No.
PhD.
Okay, maybe it was just a slip of tongue.
I think you said that you are teaching since 4 years.
No. I said probably, or I wanted to say that I am fourth year. I'm a fourth year faculty, or I'm a 4-year-old in this institute. Okay.
Oh.
That's what I wanted to say.
Okay.
Okay.
So you tell that you also study astrophysics. So
Yes.
did you also try to make up to NASA?
Well, I actually my US fellowship. I had a 2 years fellowship in USA. I was in Colorado Boulder. Okay, I was not working in NASA, but my fellowship was actually funded by NASA. Okay, so there's a program, NASA's program, Living with a Star. Okay, and I got this very prestigious fellowship, Jack Eddy postdoctoral fellowship, and so I was working in one of the NASA science goal. Yeah.
Okay.
Yeah. So NASA and so we have a lot of institutes, NOAA, NCAR, National Center for Atmospheric Research. Okay, it's a very big organization in USA, and I was a part of that institute. And yeah, it was very golden period.
Sir?
Yeah.
Sir, are you currently researching on something?
Yeah, my job is actually to research. That's why I'm not a regular teacher. No, we all faculties who don't teach too much. Okay, so that's why I know when I see a formula, I need to see the book. Okay, because like if you see, many. I mean, you all study this coaching. So they are the coaching instructor. They are not that well educated. I'm not well. Of course, they are well educated. They are not. They don't have that much degree. Okay, but we have too much degree. But we cannot, teach at that level. Okay.
Yes.
So because our we have a lot of other work. Okay, like we have a PhD student, so they work under me, and I need to discuss a lot of research problem. I also try to do independently, and then I have a collaborator in different countries, and then I have work.
Sir, what are the basic topics of research?
Huh?
So what are you currently researching on? Like, can you give us an overview?
Okay. Yeah, so much you want to know at this age. Okay, so
The topic something.
So it's the first time like we have met a scientist who is researching.
yeah, and for first few days you're thinking me as a student.
Yeah, yes, I was thinking that. Yes.
Yeah, so that is again interesting. Yeah, so my main field of research is to understand the flow inside the sun and other stars. You probably know that inside our Earth we have flow. Okay, the material is not in solid form. Okay, of course we have a core, very inner part of the Earth. Okay, which is in the solid form, and then the outer layer is so outer core, and then sorry, inner core and outer core. There are two layers. Okay, where the material is in plasma state. Plasma, this when the material when a gas or any material is heated, about a certain temperature, then the material will be will have a some free charge. Okay, so it is the plasma. So inside our sun and star, the gas is in plasma state. So I study the flow, dynamics of the material in the sun and star. Basically, my aim is to understand the origin of magnetic field. Why this astrophysical object like sun, star, other object like galaxy all have magnetic fields. Okay, so their magnetic field is produced constantly. Okay, it is not because that there is a permanent magnet. Okay, the magnetic field is produced through a mechanism called dynamo. Okay, so origin of magnetic field is my main goal of research. Okay, so I apply this research in sun, other stars, and I have also research interest in other astrophysical objects like neutron star, black hole. All these objects also have some interesting magnetic features. So I try to model those. I mean, basically, my research is theoretical and computational. We have a lot of equations that we solve by writing a numerical code. Okay. Yeah. So broad field of the fluid dynamics, plasma physics, mathematical physics, all this will be applied. Okay, in my field.
Otherwise, solving those equations,
And
don't we use these formulas?
And the electrodynamics also. I have also application of electrodynamics in my research. So what did you say?
Sir, while solving those equations, don't we use these formula which are written on the board?
Yeah, of course we do occasionally use, not regularly. Okay, not regularly we use. Okay.
Okay, sir.
But this type of formula, okay, like at least last this big formula we hardly use. Okay, so we had a formula for the velocity inside. I mean, the velocity formula that you can apply in many places. Okay, including the atmosphere in the Earth. Okay, in that equation, when I wanted to compute something from that equation, we need to use this formula. Okay, we need to use this formula. But good thing is being a researcher is that we don't have to. We have a lot of book. Okay, whenever we need something, we just open this book. Okay, and search it from internet or anything. Okay, so now we don't have to remember. Okay, the good thing in research is that we just need the creativity and the talent. Okay, and that's also true for you. Like after you complete your education, like. And many of you, your fathers is actually now developing things, developing new thing. Do they remember a lot of formula? Okay, They just sit and they just find out the formula. It's not needed to remember a lot of things, because if you remember a lot of things, your memory will be full. So talent, you need to
Yes,
define
sir.
talent. Okay, you need creativity. You need thinking. Very high thinking.
Sir, please may you tell what you were telling about direction of null vector?
Direction of null vector. Okay, so yeah, so basically, so you imagine like let's say you have started your bike. Okay, I mean, you're just starting your bike. Okay, you have pointed your direction. Okay, in that direction you'll go, but you have not started. Okay, so if your velocity is still 0, but you have defined your direction. Okay, so that context is actually like a null vector, but mathematical way to define a null vector is a vector which addition of another vector will give the same vector. Okay.
So, sir, it has a direction or it has no direction?
It has direction. Otherwise, you cannot actually call it as a vector. Okay. And if it's not a vector, then you cannot add or multiply with another vector.
Okay, sir, so it has a direction, but its magnitude is 0.
Yes.
Thank you, sir.
डायरेक्शन ऑफ ग्रेडियंट ऑफ अ फंक्शन उसमें थोड़ा डाउट हो रहा था मेरे को.
Hey, you can
Sir, null vector has a specific direction or a random direction. You
you
said.
can show your face also. Yeah, so that is the point. So the direction is not actually defined. I don't know how to whether all of you can actually switch on your microphone. So I'll actually feel good that I'm talking with student who are there in front of me. I see. Yeah, the bad thing is if you switch on your video, then your internet and the bandwidth will actually increase. So the direction is actually not defined in true sense. I need to think. So yeah, it has of course a direction, but what will be this direction? You can assign a direction. Yeah, give me some time. Let me think how to convince you. I mean, so your question, what is its direction?
Sir, no. My question is that you said the null vector has a direction. So is it a specific direction or a random direction?
Yeah, it is.
Till now we have learned that it has a random direction.
Yeah, the point is that if you add with another vector, the direction of, let's say if you add with another vector b, the direction of b will not change. Okay, so its direction will be specified only when you do some operation with another vector. Do you understand what I mean? So if you have a is a null vector, okay, and b is a non-null vector, then the direction of b, okay, this is null. Okay, so the direction of b will not change. Okay, so when you make some operation, then you can define its direction. You can assign its direction. Then A's direction will not be arbitrary. Okay, the direction will be assigned. Okay, and the vector will not change. It will be the same vector b. I mean, yeah, I mean, I'll think about it. Maybe there's better way to again represent.
That
So
means, sir, it depends on the vector with which we are doing the operation.
yes. So the operation with a null vector, I mean, the addition of subtractor will not change the vector. Okay, then. So see you tomorrow.
Sir, I have a question on the direction of gradient of a function. I have a small confusion on it.
Direction of gradient of a function, if let's say.
सर वो सिचुएशन मैं बता दे रहा हूँ, उसमें बस बता दीजिए कि वेक्टर की डायरेक्शन होगी किधर.
हाँ सिचुएशन.
हाँ सर, जैसे हम लोग माउंटेन पे खड़े हैं, मतलब बीच में कहीं हैं, तो सर वो डायरेक्शन ऑफ ग्रेडियंट ऑफ फंक्शन, मतलब फंक्शन वही माउंटेन को डिस्क्राइब कर रहा है, तो वो कौन से जगह पर होगा, मतलब वो इनसाइड ऑफ द माउंटेन होगा कि अलोंग द माउंटेन.
Okay, so that is, so the direction of the this gradient of A will be in the direction in which the steepness is maximum. Okay, yeah, rate of change of this function f is maximum. That's the direction. Now this direction can be again position dependent. Okay, at different location it will have different direction. Okay, so so let's say we have some mountain. Okay, here, and you are standing here. Okay, so again it can have direct. At this point the direction will be this way. At this point again the direction can be this way, can be this way. Okay.
और सर अगर इसके जगह हम लोग प्लेन ले लें तो उसका तो ग्रेडियंट उसके परपेंडिकुलर होगा, और इसमें अलोंग द स्लोप है.
प्लेन ले लेंगे.
यस
Plane. So plane. So in that case, you will have so for plane we have this. The height doesn't change. Okay. So then your function f is independent of space. F is independent of space, and your grad f will be 0.
Sir, but we can take the gradient of linear equation like ax plus by plus cz plus k equals to 0.
If the quantity, I think your network is poor or my network is poor. If the quantity, I mean, like if f is constant field, okay, it's constant scalar field, so that represents a uniform, plane surface, and then for plane surface, your gradient of f is 0.
Sir, let f equals to ax plus by plus cz plus k. फिर अगर उसका ग्रेडियंट फाइंड करेंगे तो उसके तो नॉर्मल वेक्टर के अलोंग आएगा.
F is equal to
ax plus by plus cz plus k.
by plus cz plus k. Okay. Now grad f is equal to, tell me.
Sir, ai cap plus b j cap plus c k cap.
C k cap. Very good. Yeah.
आप देखिए परपेंडिकुलर है, परपेंडिकुलर टू द प्लेन है वो ग्रेडियंट, और इसमें अलोंग द वो स्लोप था.
Along the slope,
सर इसमें तो z के साथ हाइट चेंज हो रही है ना?
Yeah, so in that, okay, let me remove this part. That was gradiv. So yeah, so okay, so you wanted to mean this way. Okay, so this is a form. This is a mathematical form of a plane. Okay, and grad f is actually pointing to so different location you have. How to draw this plane. Yeah, how to draw this picture. If you have a 2D plane, f equal to ax plus by, simply this one plus, let's say, k, and yeah, we have this plane x, y, z. Okay, so the f will be, so it doesn't change with z, and different point will have different. Okay, so it will represent some, it will have some value. I mean, it will be parallel to the xy plane. Okay, let's say this is a plane. Okay, of course it will not have a end point. It will extend to infinity. Okay, there's no bound. Okay, and then grad f is equal to a I cap plus b j cap. Okay, and it is I mean, this vector, what will be the direction of this vector? Let's say a equal to 1, b equal to 1. This has I and j cap. Okay, so it is pointing in some direction. Some direction it is going. This is grad f. So the good thing for the plane is that when a and b are constant, okay, this gradient grad f is uniform. Okay, I mean it is the same vector everywhere. Okay? It doesn't change because a and b are constant. Okay? So this grad f is again the parallel to this plane. So now physically, when you try to understand this function, even you can make your problem even simpler. You make your f equal to just ax. Okay, you just take f equal to ax, okay, then you know how this function is changing. As x increases, your f increases. Okay, what will be gradient of f? It should point along the x direction, and it will and its magnitude, if f is equal to ax, how will be this thing? It's just the a x cap. Okay. So grad f is telling how rapidly this function is changing, because a will tell this magnitude, and its direction is pointing along x-axis. Okay. So if f equal to just ax, okay, then it is this one. If you include the 2-dimensional, then you can again easily visualize. If you have 3-dimensional, you just visualize by yourself. Okay. Just,
Okay, sir. Sir, but the gradient of f should be in xy plane. So in that mountain example, it should be inside the mountain. The direction of gradient should be, I think,
inside the mountain. Okay, it is going inside the mountain only. Okay, the direction. But yeah, so in this case, it is not a plane. Okay, here you have this x, y, z. It is a plane. Okay, but we can have a higher order. You can the height h in that case, or yeah, this one is equal to have, let's say, x square y plus z y cube. Okay, like this. Okay, so you have a higher order. It's not a plane. Okay. So in a higher order, then your gradient depends on the location. A different point, you will have different direction. Okay, it can be this way, or here it can be this way. Here at the top, it can be this direction. Okay, so like that you have this. Okay, at the top, of course, your grad f will be 0. Okay, so that is the that says that there is a local maxima.
okay, sir. Thank you, sir.
Yeah, good point. So whenever you have a bigger, somewhat complicated form, you just try to just first understand the simple version of that form, and then you extend that form to the actual complicated form. Okay, then. So see you tomorrow, and let me end this meeting.
Thank you, sir.
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 Thank you, sir.